Okay, um, welcome to our Wednesday lecture. And before I start lecture, any questions? So, actually, I added one other playlist, digital signal processing, here, and today we will cover part of this. And in our next lecture, next week, we'll cover more. Therefore, this module, let me see. So this module will spend like week 3 and 4. So yeah, it depends on how far we are going today. And in our last lecture, we talked about the music technologies, etc. So I think the lecture today will be a practical session that I can introduce you some of the softwares here, how to use them. And also your assignment will be based on Audacity, okay? So in previous lectures, I actually used many softwares. Some of them are probably be too technical, like Python and MATLAB. It requires you of some programming skills. Therefore, they are not required. So here, I think it's best, to try some Audacity, because Audacity is not for programmer and it's easy to use. It's just some music, like audio editing software, just copy paste. As long as you have this basic operation, ability of digital computer, I think it should be okay for you to use Audacity. So here is to download Audacity to your computer. So your assignment 4 will be a practical assignment using Audacity. Okay, already published here. So another software I will be introducing is Pure Data. Okay, so Pure Data is a GUI, it's a graph user interface. Okay, it's for like computer human interaction. So the interface will be like this. So it's also of this higher level programming, languages. So and it's also easy to use. It's a standard kind of software. It's developed by Professor Miller Pocket at UCSD. Yeah. So but he already retired. Yeah. But this software was developed by Professor Miller Pocket, and it's a standard kind of software, used in our computer music teaching for undergraduate. So basically, if you are like I mean like the third year of undergraduate, you should be able to use this software. Yeah, it's not required in this class, but I will introduce this interface and show some of these objects and how do you manipulate this. And this is also open source and free. I would recommend you to download this software also. And if you'd like to, you can just, maybe do your final project using this software. It's totally acceptable. Let me see. Okay. If you click this, so this is Professor Pocket, his website. And here you can download this. You can see it's compiled for Windows 64. So this is what I download. Yeah, because I use Windows. If you use Mac, like here, probably OS, so you can find all those, stable release older systems. So this should be stable release. Okay, this is for Mac. This is for Microsoft Windows. This is open source, and if you take course like 171, music 171, 172, you will use this software extensively. And another software is Max. So we won't use Max because I personally don't use Max, but Max and Max and the pure data, actually they are of the same kind of operating system, you know. Yeah, but Max is actually more like commercially oriented. Therefore, you need to buy it, right? You need to pay for it, and this interface looks like more fancy, but this internal operational system is the same. Okay, you can see these just some objects and some lines. You just link these objects together. It's the same as PD, but PD is more like yes, the interface is not that fancy. It's more plain, and it's free. Okay, but for Max, it's commercial, and there are like many people use this, and because people buy it, subscribe, pay for it, therefore they developed many like built-in libraries. So if you want to be a music producer or music programmer, Max would be something like, yeah, if you'd like to pay for some already established software. But me personally, I don't use Max. And it's the same operational system as PD. So if I introduce you PD, I teach you how to use PD. Yeah, it can be easily transferred to Max. Okay. So this is the Max interface. So I will take some time, okay, to talk about how to use Audacity and how to use PD, okay, pure data. I will introduce those interface, and if you have any question, you can just ask. If you have anything, you are not sure, you can just ask me in time, okay? And if you like to, you can download those softwares and just operate with me when I operating. And also because this video is recorded, you can always go back, okay? You can always go back and check the what I did using those software, and you can just see where you did wrong, or if there's anything unclear. I think you can just check it. Okay. Any questions? Okay. So if there's no question, let me just start talking about the digitalization of sound. Okay. We will go through those concepts slowly, and I will show you all of those kind of concepts, those things practically using the software. So first, like what I said last time, I will recommend you to read this book. Okay, this book is in our module here. It's Introduction to Digital Signal Processing. So it's a very low-level introductory book to digital signal processing, and not really require you of any particular knowledge, prior knowledge. Okay, it's written for musicians and not not with strong STEM background. So I think this would be a good book for anyone to read. So I will use this book. I will talk about this sampling, okay? So we talk about the sampling, the art of being discrete. It's in the chapter 1, subsection 4, okay? Okay, so I hope you can read those texts by yourself, but we already talked about something about being discrete and digitalization. So usually, so we talked about sound waves, right? So we know sound waves in the air. So when I produce the sound wave, when it transmits in the air, it's continuous. It looks like this, right? It's something continuous. But when you use computer to record this sound, actually it looks like this, okay? So if you look at it far enough, it seems to be continuous, but if you really zoom in, it's discrete. So how can you visualize this in Audacity? So let me get to Audacity now, okay? So this is the interface. I think yeah, our interface should be similar. Actually, I downloaded the old version because the new version doesn't really compare with my system. Yeah, if you have the newest Windows system, there might be some problem to compare with all the newest release of audacity. I don't know if it's my problem or not, but I used, yeah, therefore I just choose to use some old system that's compile better with my computer, but the basic system, okay, the basic interface should be the same. So when you get to this interface, okay, this plain interface, what we will do is that I will create a track, okay? So you can see there is file, edit, select, view, transport, tracks, generate, effect, analyze, tools, help. So I will basically talk all of those functions, okay? So first we'll talk about tracks. So add new. So you can choose to add a mono track or a stereo track. So a mono track is just one track, okay? A stereo track will be 2 tracks. Okay, so you can see there are 2 tracks. Actually, the stereo means left and right. So because you have 2 ears, so it's just left and right. But for mono track, it means when you listen to this track, what you hear from your left ear and right ear are the same. Okay. So here for our purpose, we'll first use a mono track. It's just easier to visualize. Okay, easier to use. What I will do is that another thing we will use extensively in this lecture is to generate a tune. Okay, so if you go to generate, there are many different things you can generate, like chirp, noise, silence, tune. Okay, these are in Chinese. Because yeah, as I said, I actually converted my Audacity to the older system. Therefore, there's something I choose the system to be in English, but something still in Chinese. So yeah, it won't affect our teaching. So just don't worry about this. So let's see, what if I choose chirp? Let me generate a chirp. What is this? Okay, let me play this. So play is this button. Okay. Maybe let me move this a little bit like here. Play this. Okay. So yeah, I think this is a chirp, like the pitch is sliding up. So back to what we just talked about, right? We want to visualize this digital audio or discretized. So if you look at this graph, you cannot tell it's continuous or discrete, right? So what we are going to do is that we will actually choose a piece of that and go to here, okay? This is called fit section to width, right? And it's still not clear. We just zoom in more, okay? Zoom in more. Okay, so you can see it's still like continuous. So this is zoom in, right? What about we do more, right? So suddenly you can tell that from here to here. So when you really zoom in, you can see all the waves actually discretized, right? They are of these discrete points. And if you zoom in more, you can see these points clearer, see them better. So in Audacity, there is a function called draw. So it's this draw tool. So use this draw tool. Actually, you can change those points, separately. I actually don't know why they designed this tool, because there are so many, every second you have 44100 points. Therefore, I don't think that changing those individual points will actually have a great influence in the sound you hear. And it's difficult to determine like what this will sound like, okay? But I don't know why they do this, but they have this kind of convenient tool that you can actually change those individual points by hand. Yeah, although I'm not sure how practical this function is, but it's something you can do. You can change those discrete points here. And here, when we generate this track, you can see here are some basic information here. Like this is the sampling rate, okay? 44100 hertz. So it's 44K and 100 hertz, right? Yeah, it's just how I read the number. But this is a sampling rate, which means there are so many this many points per second. Okay, and this is 32-bit. So you can see these are two numbers. Okay, so we're going to talk about what these numbers represent and how do we understand those. Okay, so this is when you zoom in, this is the discretization of sound. So let's continue with this. So after you zoom in, you can see here, right? This is fs. Fs is the sampling rate. So in this Audacity, the standard sampling rate is 44100 hertz. Why it is this number to be standard? We will also talk about this. Okay, why people choose this number to be the standard sampling rate for all the audio systems. And now let's continue with this. So this sampling rate it's still kind of frequency, and the frequency is the 1/t is the period. So what is t here? So t is actually the distance or the the time interval between the two consecutive points, right? Between the two consecutive points, sampling points. So this is t. T is 1/fs, right? 1 over the sampling rate. So it's time in samples. And now you can see your time is discretized, right? So when you talk about time, you can only talk about time like this, which is the integer multiple of the interval, right? So for example, your t is, for example, your t is 0.1 second, and then all the time you can have is the integer multiple of this number, which means you can have a time of 2.002. You can have 0.3, but you can never have a time stamp like 1.15, okay, 0.15, because this is not an integer multiple of your time interval. So this is the effect of discretization, right? So once you discretize this, then all your time is discretized. Therefore, you cannot have any point in between. So in between these points are these intervals are void. Therefore, you cannot have any points, any number here. Everything is discretized. It's just for this fixed interval. And here it gives us the sine, right? The sine wave is 2 pi ft. And after you discretize the time, you just replace this time t with nt. Okay, so this is discretization. And some calculation here, not important. So here it actually tells you how to use MATLAB to generate this, but we're not using Audacity. It's the same. It's the same. Okay, so how to use Audacity to generate a sine tune like this? So now you go to this interface. Okay, let me go back to this function. Let me delete this track. Okay, so this track is okay. Seems doesn't work. Okay, let me reopen this Audacity. Okay, so how do you generate a sine tune? Just go to generate. Okay, so for first, maybe you just add a track. Okay, a mono track will be enough for a sine tune, and generate a tune. Okay, so it's tune and sine. So here are different waveforms we are going to cover later on, but for now we're just generating a pure sine tune. So you can choose the frequency, let's say we want the frequency of 440. Okay, so it's A4. And amplitude, maybe 0.8. And duration, okay? So we can choose, so this is second. We want to generate maybe 0.6 seconds is enough. Okay. And let me play this tune. Right. So this is a sine tune of 440 hertz. Let me zoom in this tune. Okay, so you can see this is a pure sine tune of this is the sinusoidal wave. Okay, so if we zoom in more and more, it's still discretized. Okay, so here is the sine tune. And in Audacity, you can choose different, frequencies, amplitude, and those numbers. Okay, so let me skip this part and maybe go to the sampling theorem. Okay. So sampling theorem basically means like why we choose this number, okay, to be our standard sampling rate. So instead of just talking a lot about those, maybe let me go back to here. Okay, let me just let's look into those effects from this practical example. Okay, so here I have this track. Now I want to add a new track. Okay, so in this new track, what I will do is that I will change. So if you go to this audio, and then you can change different options. There are different options. You can go to rate. Okay, so at rate, you can change different sampling rate. So now we have the standard rate is this number, but we can actually change this rate to a higher number or a lower. Let's say we choose this lowest, 8,000. And let's see what will happen. Okay, so again, I will generate a tune the same as before, okay, at 440 hertz, and this number, and okay, and let's listen. Okay, so now when I click solo, it only plays the first track. Okay, let's listen to this. So when I solo the second one, okay, so you can hear the in this auditory or perception, they are of no difference, right? They sound exactly the same, and they look actually also kind of similar from this kind of view. But what if we zoom in? Okay, right. So okay, let me be here. So here you can see, you can tell they are of the same period, right? Because they are of the same frequency. They are of the same period. Let me zoom in. So when we zoom in, you can see here, it is still somehow continuous, but here you can you already see those sampling rate. Okay. But what if I zoom in more? Okay, so here you can see they are of the same period here, right? This is one cycle. And obviously in this higher sampling rate, there are more points. But in this lower sampling rate, they are just, very sparse. The points are very, very sparse. So this is the effect of different sampling rate. Okay. So because our tune is 440 hertz, it's actually really comparatively low comparing to either 8,000 or 44100 hertz. Therefore, they have no difference, produced using these two different sampling rates. But what if we generate a different tune, right? You can try it with different tune, but let me see what I will do. Okay, about this, let me generate a new track. And let me still change this rate to 8,000. Okay. So now what I will do is that I will still generate a tune. Let's see, what if we generate a tune of 2000 hertz? Okay. So when I generate this 2000 hertz tune, you can see the sampling, right? So this is one cycle. This is one cycle, right? So every cycle, it only has four different points. Because your tune, your sampling rate is 8,000 and your tune is 2000. Therefore, you only have 4 points to represent one cycle. Yeah, I don't know if it's clear, but okay, probably we should talk more about the theory before I talking about those Okay, let me skip this sampling theory for now because we will watch a video talk about this. So let's continue with the graph. Okay, so here it talks about the same point, right? When you use different sampling rate, so you will okay, no, it's not different sampling rate. So it's 1 hertz. So your frequency is 1 hertz. Here your frequency is 5 hertz. Under the same sampling rate is 100 hertz. So this is the graph you will get. And what if you change it to 20 hertz, right? And then you have much less points to represent one cycle because your frequency is getting closer to your sampling rate, okay? And continue with this. When you choose a frequency, like almost a half of your sampling rate, okay? So it's almost 50 hertz, so you'll get something like this. So here you can compute that because it's almost the half, so you only have 2 points to represent per cycle, right? So for example, I have a sinusoid sine wave, okay, like this. So this is one cycle of sine wave, right? So normally, if you have large enough sampling rate, you can sampling this wave like by many points, so that it's like well represented, right? You know it's a sine wave and you know this shape because you have enough points. So the problem is that now my fs is 100 and my frequency is almost 50. Therefore, for each of this cycle, I only have 2 points, okay, to represent this cycle. So the best I can do is that for this cycle, the best I can do is that I will choose, right? I will choose 1 point here, I'll choose 1 point here. So when I choose those 2 samples, it will give you a graph like this, right? So all the points are at the highest amplitude. So positive, negative, positive, negative. So it's like this alternating kind of current. Therefore, here it's already lose the shape of this sinusoids, right? So actually we can visualize this also in Audacity. Okay, so what if we have a sine wave at f equals 50 hertz? It's a line. Okay, it's a line because as I just drawn, right? If you have a cosine wave, you can choose these 2 samples. But if you have a sine wave, the only thing you can choose is this and at half, right? And this one, because for sine waves, the half of the cycle is 0. Therefore, it gives you a line. A line, it means there's no tune. This will be no sound. Okay. So let me do this. Let me do this here. Okay. So now we have a sampling rate of 8,000. So half of 8,000 is 4,000, right? So let me generate tune. Let me choose 4,000. Let me generate. Okay. So I was draw in this graph. it gives you, just a line. Because actually here, what you really want, here is actually like this, right? So the tune is like this. This is your 4,000 hertz tune, but because your sampling rate is too low, therefore you only have 2 points to represent each cycle. Therefore, it gives you a line, right? So if we listen to this tune, we can easily predict, right? This will be there will be no sound. Let me solo this and play. Okay, there's no sound. But what if we generate this same tune, right? This 4,000 hertz tune. Okay, maybe let me rename this track to 4,000 hertz. Okay. So now let me delete those things and add a new track. And this track will also still generate a 4,000 hertz tune. Okay. But this track has this sampling rate much higher. So let me generate tune. Okay, it's 4,000. Let me generate. Okay. So let me first play this tune. Okay, so this is 4,000. There's sound, there's waves. Let me zoom in. Okay, so from here, zoom in more, you can see actually they are of the same period, right? Let me draw this. So this is one cycle. This is one cycle, right? So these two tracks actually of the same period, the same frequency, because we choose the same frequency, it's 4,000 hertz. But because this track doesn't have enough, sampling points, therefore it can only generate 2 points per cycle. But here it has like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, like 11, 12 points. So this is sampling rate. So I hope that this should be somehow clearer for you. Okay. So remember, what we just talked about is that we reached the half of sampling rate, right? But the question is, what if we pass this number? What if we have like 60 hertz or 80 hertz here? What the system will generate, right? What the computer will generate. So here is a demonstration. So here it gives the frequency at 95 hertz with a sampling rate 100 hertz. So it gives you a somehow okay, wave. And if you compare this graph with a graph we just saw here, actually they are the same sampling graph. Okay, so this is a 5 hertz. Okay, so remember this graph, and if you view this one, so they are actually the same. So the effect is that when you have a sampling rate of 100 hertz for a given tune at 5 hertz and 95 hertz, they are actually producing the same sound, the same tune. Why is it happening? Right? Why is it happening? So it's actually called aliasing. So the aliasing actually, easily speaking, is like this. Okay. So for example, here this is hertz. Okay, this is frequency. This is hertz. And this is, let's see, this is 100 hertz. It's your fs, okay? 100 hertz is your sampling rate. So, okay, so normally, if it's not your sampling rate, okay, for any continuous, let's say we have a continuous tune for 100 hertz, of course, what we will listen to, what we'll hear is linear, right? So when the frequency is 0, we hear a 0 hertz tune. When the frequency is 100, we hear a 100 hertz tune. Okay. But the problem is that for sampling, because we have a limit, which is sampling rate. So when we set this 100 to our sampling rate, fs, what we will read here is that for the first half, okay, from 0 to 50, we will hear exactly the same. Yeah, the normal tune, right? When you give 30, I hear 30. When you give 40, I hear 40. The problem is that once this limit past this half of the sampling rate, this line will actually fold over. Okay, this line actually will just go down, which means when you give me a 60 hertz tune, I won't hear 60 hertz. What I will hear is it's 40 hertz. Okay. And when you give me a 90 hertz tune, what I will hear is 10 hertz. And everything, let me choose another color. Okay. Anything from this part, okay, anything above 50 hertz, in this part is called alias. Okay, it's called alias. Alias means this is wrong, right? This is not the real reflection of the frequency. Because when we expect to hear a 60 hertz tune, we don't hear 60 hertz, we hear 40 hertz. When we expect to hear a 90 hertz tune, it only generates a 10 hertz tune. Okay, so this is aliasing. Before I do this experiment in Audacity, let's watch a video together. Okay, I think it gives you a better maybe illustration of alias. Okay.
If your sampling rate is too low, you may have a problem called aliasing. Let's say we want to convert this wave from analog to digital, and we sample it like this. By connecting the dots, the samples are going to produce this, which looks like a sine wave with a different frequency than the original. That is, the digital wave has a different frequency than the analog wave we tried to measure. When this happens, the original wave cannot be recovered, so we would have to re-record it with a higher sampling rate. Therefore, it is important to avoid this from the beginning. This is a graph showing the frequencies of the original wave and the reconstructed wave. For simplicity, we will say that our sampling rate is 1000 Hz. Ideally, we would want this graph to be a diagonal line. That is, that the reconstructed frequency is always equal to the original frequency. In a certain range, this is going to be fulfilled. Here, it would be from the beginning up to 500 Hz. After that, if we keep increasing the frequency of the original wave, we will start to reconstruct lower frequencies. This means that we are not getting the correct information. After 1000 Hz, the reconstructed frequency starts to rise again, but it is well below the frequency it should have been. An interesting case is when we have an original frequency of 1000 Hz and a sampling frequency of 1000 Hz, which gives us a reconstructed frequency of 0 Hz. When the original frequency and the sampling frequency are equal, we will be taking exactly one sample per cycle. So, we would be reconstructing a horizontal line, which is considered a frequency of 0 Hz. In the case of having an original frequency of 500 Hz and a sampling frequency of 1000 Hz, we would be taking exactly 2 samples per cycle, which gives us a triangle wave. Although it is true that it is a different waveform than the original, at least it still has the correct frequency. So, with a sampling rate of 1000 Hz, 500 Hz is the maximum frequency that we can sample without aliasing. Another example with this sampling rate is that if we try to sample a 700 Hz wave, we will get a 300 Hz digital wave. This would look like the first visual example I showed. In this region, there is another way in which we can visualize aliasing. It's as if the original frequency reflected around 500 Hz, which here gives us the 300 Hz. We can describe all of this behavior more generally if we replace the frequencies by factors of the sampling frequency. So, we can see that the only range where we can reconstruct the correct frequencies is from 0 Hz to half of our sampling rate. And after that, we have aliasing. This important fact is known as the Nyquist theorem. And the frequency equal to half the sampling frequency is known as the Nyquist frequency, which will be different depending on the sampling frequency.
Okay. So we'll talk more about this. So if you still like confusing about this concept, this is fine. Okay, this is fine. Because I think now it's good time for us to maybe do some exercise after I talking about this digitalization. Okay. So again, like between the difference between analog and digital, right? So a signal, okay. So maybe let me skip this. So continuous time signal is analog. Okay, analog signal is continuous. So continuous time mean if there is a sound of 2000 Hertz, we'll hear 2000 Hertz. If there's a sound of 20,000 Hertz, we'll hear 20,000 Hertz. Okay, in real life, I mean in real life, if we don't go through put the sound through the computer system. So if there is a sound of 40,000 Hertz, we will hear 40,000 Hertz. But the problem is that because the human hearing range is from 2 to 20 Hertz, right? It's from wait. It's from 20. Oh, wait, sorry. It's from 20 to 20,000 Hertz. Okay, so this is the human hearing range. So if there is a tune of a frequency like 40,000 Hertz in real life, in nature, we will call it ultrasonic. Okay, so it is presented. It is presented in nature, in our life, but we never hear this sound like in using our auditory system. But for other animals like the whale or dog, maybe they will hear this sound. But for human, we don't hear this sound, but they are presented in all the sound. Okay, because if you are listening to some sound, there's very, very low frequency, even below 20 Hertz, something, larger than 20,000 Hertz, they are presented, but we just don't perceive it. So the problem is that if we have a sampling rate, let's say our sampling rate is of this number, then we'll hear all those sounds in our perception system as the original, right? Presented in nature. But the problem is that when any of the sound, ultrasonic sound frequency present in the sound, in nature, for these continuous time signals, we won't be able to hear them. But if we put through everything through a computer system, we sampled it, then because of aliasing, all those frequencies, all those ultrasonic frequencies will actually fold over, okay? So they will actually reflected back. So they will fold over. So let's say if there is a sound of 60,000 Hertz, so we will still hear it, okay? So let's see, if there is a sound of 70,000 Hertz, so naturally speaking, we should never hear this high frequency. But in computer system of fs equals 40,000, we will hear this sound as what? As 10,000, right? And we will hear this sound as 10,000 Hertz. So this is the aliasing. Aliasing means you just get all those, even so there will be also negative frequencies, like negative 100 Hertz. It is also presented actually. It's just we don't define the negative frequency for now, but all the frequencies in the frequency range from minus infinity to infinity will be fold over into this limited range, and we will actually hear all those sounds presented. And these sounds will kind of interfere, interact with each other, and this will be a problem, right? Because it's not a faithful reflection of what's presented, to our ear by the analog signal. So whatever, let's continue with the discrete time digital signals. So here you can see you use this, discrete points to sample a continuous waveform. And there is something called analog to digital conversion, right? ADC. And there will be DAC, digital analog conversion. So when you convert something from analog to digital, it goes through two tasks. Okay, one is sampling. This is what we are talking about now. Another is quantization. Quantization is our next topic. Okay, so now let's focus on sampling. So sampling, we talk about sampling rate, sampling period, and time discretization. Here are some exercises. So maybe let me go through this, okay? Do some basic arithmetic so you have a better understanding of what we are talking about. If you are not very sensitive to numbers, it will give you some buffer, to understand this concept. So let's say our phase is 16 Hertz. What's the duration of this signal? So you can see in this signal, so this is one cycle, right? This is one cycle of cosine. How many points are here? You can count, right? 1, 2, 3, 4, 5, 6, 7, 8. So there are eight points, 8 discrete points representing one cycle. Therefore, let me see, what is the duration of the signal shown? Okay. Let me find the annotation. So your FS is 16 Hertz. And now your question is, what is the frequency, right, of this sine wave? So before computing the frequency, there are actually 8 points per cycle, right? 8 points per cycle. Yeah, let me see, how should I explain this? So actually 16 points represent 2 cycles here, right? Which means every second it goes through 2 cycles, which means the frequency should be 0.5 Hertz. Okay. Maybe I'm calculating too quick here. But let me see, how should I explain this? Because FS is 16 Hertz, which means there are 16 points per second, right? So here, from here to here, this is in total 6 points. So this is 1 second. 1 second. Therefore, your 1 cycle is 0.5 seconds. Okay. Oh, it should be 2 Hertz, sorry. It should be 2 Hertz. So this should be 0.5, the duration. Or there's no duration, it's the period. Okay, the period is 0.5 seconds, and it's 2 Hertz. So it's 2 cycle per second, right? It's 2 cycle per second, so this signal should be 2 Hertz. Therefore, your F equals Fs divide N, right? N is the number of points in each cycle. So here N equals 8. Fs equals 16. Therefore, you have 2 Hertz. Okay, so this is the formula to compute this. So here I ask the duration, which means the total duration. So here is 1, 2, 3, right? It's 3 cycles. Therefore, so the period is 0.5. So 3 times 0.5 is 1.5 seconds. Okay. And asks, what if fs is 32, the duration is shorter, right? It's half the duration. Okay, if the frequency we just compute is 2 Hertz, right? So 16 samples corresponds to 1 second, and there are 2 cycles in 1 second. The frequency is 2 Hertz. Okay. So this gives you some numerical quantities of the relationship between sampling rate, frequency, period, etc. Okay. Sampling and reconstruction. So here it's the same graph as I showed in Audacity, right? So this is a continuous sinusoid, and if you have fs at 32, it gives you more sampling points. If it's half, then it gives you half points, right? It just skip those points in between. So the sampling points are like much more sparse. Okay. So just some math problems. Sampling in practice, frequency. Okay, so yeah. So this is what I want to talk about. Okay. So here, so this is like aliasing. Why the aliasing comes? Okay, why it happens? So we just saw in the video, and also as said, right? There is a fold over. So in real life, it should be a diagonal line for like the real frequency and the frequency you hear. Okay, but for given sampling rate, so this is the half sampling rate. Okay, fs over 2. So this actually this line fold over. So why it folds over? So this graph gives you an illustration. Okay, so this is actually gives you what happened at this point. Okay, at this half point, because this frequency is half of the sampling rate. So once your frequency pass the half sampling rate, your point will go here, okay? And then in your next point will go to somewhere like further. Like here, over here. Therefore, you have an alternative like lower frequency, right? To link these points together. Yeah, I'm not drawing really good, but you can read this graph. Okay, so you have an alternative frequency that's of lower frequency than the original one, right? So this is your original frequency in blue, but there is an alternative one if you choose a frequency that's higher than half of the fs. Okay, so this is where the aliasing comes from, and this is why it folds over. Okay, so here let's see, gives you better illustration, right? If your sampling is like undersampled, there's too few samples to represent, then you cannot like really know like how many circles are there, right, in between. Therefore, maybe just choose the easiest one, the lowest frequency here. This is where the aliasing comes from, and this is folding over. We just talked about. Okay, so this is the folding over, the Nyquist limit, etc. So comparing to those concepts, okay, so I think we just briefly went through the concept, but even if you don't understand the math, it's fine. I mean, we just do the experiment, okay? We just watch and listen using your eyes and ears, and then you will believe what was really going on. Yeah, if you don't want to do the math. So let me see. Okay, so again, let me create a new track here. Add a mono track. Still change the rate to 8,000. Yeah, choose 8,000 because it's convenient. Okay, there's no like specific reason why I have to choose 8,000. It's just convenient. It's just some experiment. So now let's say we want to generate a tune, probably 3,000. Okay, so 3,000 is lower than half of the sampling rate, right? It's lower than 4,000. Therefore, it should be a faithful representation of this sound. Let me solo this and okay. Let me play this tune. Okay, so this is a 3,000 hertz tune. Okay, then let me generate a new track. Add new mono track, and again let me change the rate to 8,000. Okay, so you can see here is 8,000. But here I want to generate a 5,000 hertz tune. Okay. Let me generate a tune of 5,000 hertz. Generate. Okay. So let me listen to this. Okay, so obviously these two tunes actually they produce the same sound. But the problem is that what I'm doing here, right? What I want is a 5,000 hertz, but it generates a tune the same as 3,000 hertz. Now let's zoom in and see the waveform. Okay, so you can see the waveform here. They are basically the same. Okay, they are basically the same. It's just the starting point is somehow a little bit different, a little bit off. What if I do this, right? Oh no, not really. Maybe I should do this. Yeah. So you can see the exactly line up with each other, the two tunes. But now what I want to do is that actually I can add a new track, but this time I'm not going to change the rate. I will leave the rate as 44100 hertz. And again, I will generate a 5,000 hertz tune. Okay, generate tune 5,000 hertz. Generate. So you can see this wave like becomes much more dense, at least. Let's hear this. Okay, so this is the 5,000 in this rate, and this is the 5,000 in this rate. So obviously this 5,000 is more like 5,000, right? So this is the 5,000 again. Okay, let me zoom in. Let's see the difference. Okay, so obviously this one have more like sampling points. More sampling points. And if you draw this waveform here, I believe after you viewing this thing, you should draw something. Oh no. Draw something like this, right? I'm not drawing really good, but yeah, you know, the feeling, right? You know, this is somehow like this, you know. Yeah, at this rate. Here, actually, if you compare these two graphs, I mean, you can also draw it something like this. But this is alternative. Um, the real thing happens here is that I think it's actually, okay, this is so difficult to draw. Yeah, I don't know if you can understand this or not. Okay, let me see. Hmm. Yeah, what I want to show you is the Aliasing. Okay, so when you view this graph, probably what you would draw is something like this, you know. Okay, I should go through these points, but here, yeah, seems not that correct. Let me try again. Oh, yeah, it should be like this. You see, from here to here to here, and then you go through here, and then you go here. Okay, and then you go there, and then you go there. Somehow like this, okay? So this is the frequency actually kind of produced by this wave. But an alternative way is to draw it like this, right? So an alternative way would be, so here I already go there, right? I already went like a quarter, and I go here, and then I come here, and then I go here and go here, and do like this. Okay, so for this yellow line, it's the same as this one. Okay, it's the same as this real 5,000 hertz. But because this in this graph, it's downsampled. It has too few points. Therefore, you cannot even you don't have points in between. Therefore, you cannot determine which frequency it presents. So so the system actually choose this red one, which actually gives you actually 3,000 hertz. Okay, so this is aliasing. This is what you can draw from the graph. Let me see the chat. Yes, yes, yeah. Yes, here. So this is 8,000. This is 44100 hertz, and they actually sound different. Okay, so this one sounds like this, and this one sounds like, okay. So this next one is obviously real 5,000, but this one is alias. It becomes 3,000. Okay. Okay, I think this gives you a kind of okay demonstration of alias already. So let me see. So there are some other things I also would like to address, but before that, okay, you don't need to do it now. Before that, let's watch this video. What happened? Okay, so here is another well-made video, and it also used Audacity to show you the demonstration. Okay, so
What's the
it talks about the sampling theorem. Okay, the sampling theorem, the Nyquist limit in more like detail. Actually, what's the sampling theorem is talks about like is more like fascinating. It's actually it tells you for whatever shape of the because like maybe you will wonder, right, why we always use these sinusoids, because for a wave like this of the same period, I would say we can have a square wave or a triangle wave, or we can have a square wave like this. So they are of the same period, right? And the wave can be of any shape here, as long as they are repeating at the same rate. But why we are not hearing this kind of waves, why we are always hearing the sine wave? So this is what the sampling theorem tell you. Yeah, because it filters all the higher frequencies, and yeah, it always it always choose the sinusoidal points, whatever. Yeah, so I will play this video, and it gives you a better like illustration, like deeper illustration, I would say, of this sampling theorem, and the digital audio converter like that.
right number? How many samples are enough to accurately represent this wave then?
I don't know how can I get rid of this, right? Maybe let me try this.
Well, thankfully, it's not as arbitrary as you think. Continuous to discrete signal conversion is governed by the Nyquist-Shannon sampling theorem, which states that any band-limited continuous time signal can be accurately converted to and from digital signals when sampled at a rate at least twice as high as the highest frequency component of the waveform. Sounds complicated, but let's break it down. The sampling theorem states two important facts. One, that to represent an analog signal in the digital domain, the number of samples we would need for each second of the signal should be more than the highest frequency represented by the signal. If a signal has a 10 kHz frequency component, the sampling rate needs to be more than 20 kHz. It also states that the analog signal needs to be band limited to the highest frequency and cannot contain any frequencies above that. Let's put a pin on the second point and just talk about the first. In our case, we had a 1 Hz sine wave. This is a constant 1 Hz wave, and 1 Hz is the highest frequency that this wave function will ever produce. The sampling theorem states that to digitally represent this wave, we need at least more than 2 samples. Let's say 3. Any more is fine as well, but the minimum required is 3. We can say that the sample rate is 3 Hz. Hertz is an overloaded term here, and not to be confused with the frequency aspect of the wave. The reason that both cycles per second, which is the frequency, and samples per second, which is the sample rate, have the same derived unit of Hertz is because they both represent the same basic unit of 1/seconds. This is how a 1 Hz wave could be sampled using 3 sample points. You might wonder at this point that 3 points are clearly not enough to represent this wave correctly without losing a lot of resolution. I mean, if this sample waveform would have to be converted back into the analog signal, there is room for interpretation, right? The signal could be rendered in several different ways. Surely, if the 1 Hz wave were to be sampled at, say, 40 Hz sampling rate, there would be less room for divergence, and you'd get a more accurate representation, right? Well, the short answer is no. This is where a lot of misconceptions of higher sampling rate equal to better audio comes from.
The absolute beauty of the sampling theorem is that it proves mathematically that both 3 Hz sampled waveform and 40 Hz sampled waveform of a 1 Hz wave, when reconverted back into its analog form, doesn't just produce the same output signal, but produces a signal which is indistinguishable from the original analog input signal before conversion. The input and output signals would essentially be carbon copies of each other with no loss in resolution. This seems really strange and unintuitive because you're essentially stripping out information and discarding it when converting it into a digital signal. And then when you reconvert it back, how is this missing information magically reappearing? Well, this is where the second point comes into effect. The signal would need to be band limited. This means that an input signal going into the conversion process is stripped of all frequency components above the maximum of 1 Hz, and the digital signal, once reconverted, is again stripped of all frequency components higher than the maximum of 1 Hz. This can be accomplished by using a low-pass filter. A theoretical low-pass filter would only allow the passage of frequencies lower than a set threshold, and would block all frequencies higher than the threshold. I mentioned a theoretical low-pass filter here, since practical filters can't simply cut off abruptly at a certain frequency, but rather ramp down smoothly. More about this later. But let's now look at a more audible example. I'm going to use Audacity to demonstrate some of the examples here. If you haven't heard of Audacity before, it's a free and open source digital audio editor, and you can download it from the link below. I'm going to change the project sample rate to a low value. I'm going to choose 8,000 as the sample rate. So according to the sampling theorem, we've learned that we can only hope to represent frequencies below half that rate. We can represent frequencies till 4,000 Hz and no more than that. Let's try to generate a sine wave, and we'll go to Generate and Tone, and we can choose a frequency here. You can see that Audacity will not let me generate a tone higher than 4,000 Hz. We'll bypass this failsafe later and see what would happen if we were to choose a frequency over half the sampling rate. But for now, we'll choose something more sensible. Say 1 kHz. Well, it sounds like a 1 kHz signal. We can quickly select a bit of the audio signal, go to Analyze, and plot spectrum, and we can indeed see that it represents a 1 kHz pure tone. I'll admit, this is a bit of a cheat, because we're not generating an analog 1 kHz signal and digitizing it, but rather building the sine wave in the digital domain and then sampling it. But it's fair to assume that the end product is the same. And without having a physical analog signal generator sitting beside me at this moment, this will do fine. Now let's explore the fringe of possible frequencies. 4,000 Hz, exactly half the sampling rate. Audacity lets us do this, but where's the signal? You can play it and you can plot it, but the signal is nulled out. Nothing exists. This is easy to illustrate. Let's take a 4 kHz signal and only sample it twice a cycle. This is the current situation. All sampled points, unfortunately, sit at the zero valued point of the signal. So naturally, this is interpreted as no signal at all. But increase the phase offset of the signal by just a bit, and suddenly the wave comes to life. So this is the reason why the sampling theorem states that all frequencies lower than half the sampling rate can be represented accurately, and doesn't say anything about exactly half the sample rate, because it wouldn't be an accurate representation for all scenarios. So what about 3,999 Hz? That's lower than half the sampling rate, right? Let's find out. In Audacity, we'll generate a sine tone of 3,999 Hz. You get this bizarre output where the amplitude is modulating from high to low and back constantly. Surely enough, you can hear the 3,999 Hz signal, and the frequency plots say so as well, except for the fact that the amplitude is all messed up. I'll try to explain this in a little while, but let's push on and push up the sampling rate. We need to create a new project in Audacity because you shouldn't have audio signals of different sample rates in the same project. In this project, we'll select our sampling rate to be the next available value of 11,025 Hz. and will produce the same 3999 Hz signal. This signal is comfortably below half the sample rate, and it's reproduced quite well. No weird modulation. The plot shows the correct frequency as well. Now let's zoom in. Yeesh, that looks pretty bad. And in no way does that look like a sine wave, or even a periodic function for that matter. But the strange part is that it's generating a pure sinusoidal tone of 3999 Hz. Let's repeat this exercise for a sample rate of 44,100 Hz. Generate the same tone and zoom in. That looks more representable, has better resolution because of more data points, but it produces the same tone. No perceptible change whatsoever. What advantage do we have then when changing the sample rate from 11,025 to 44,100 Hz? We got more data points, but no general increase in quality. Of course, with a sample rate of 44,100 Hz, you can represent more frequencies than is possible with a sample rate of 11,025 Hz. But for the specific frequency of 3,999 Hz, it offers no advantage. I'll repeat the same exercise for much higher sampling rates, first at 96,000 Hz, and then at the preposterously high 192,000 Hz. And I'll lay them all together so you can hear the difference for yourself. Convinced yet that there...
Right, so the point here is that he's talking about as long as your sampling rate, right? I mean, as long as your frequency is lower, so this is your frequency, as long as it's lower, fs over 2, right? Half of your sampling rate, then no matter how large your fs is. So here he uses f of 3999, right? And fs can be these different numbers. So as long as your fs is equal than like 2 times 399, then no matter your wave looks like this, right? This is really like rugged, or it's like barely smooth, or yeah, okay smooth and extremely smooth. So usually you will think, okay, I have a very, very high sampling rate, and this wave looks very, very much like sine tone, right? Because we are producing a sine tone now, so this wave looks like the perfect sine tone. So this should sounds better than this one, right? But because this one looks like not like sine tone at all, right? It's like there are many like these weird lines, and this looks no way like sine tone. But the problem, not the problem, but the result is that whether this tune or this tune, actually they all produce a 399 Hz pure sine tune. Okay, so this is the point this author is trying to illustrate using the sampling theorem. Okay, and you can also do this experiment in the Audacity yourself. Okay, in your homework, it will be an interesting homework to do, because when you, for example, if you have fs of 8,000, okay, so probably let me do this. Okay, because he actually,
There's no difference.
let me generate, okay, let me add a new track and change the rate to 8,000. And like what he did, let me generate a 3999 Hz tune. Okay, just generate tune, change this to 3999, generate. So you can see here, because I'm generating too short. Okay, it's too short. Let me change this to probably 2.6 seconds. Okay, and you can see here, yeah, it's of this form. And if we listen to this, it produces no sound. I don't know why. Okay, maybe I know why. Let me zoom in. Okay, let me zoom in this thing. Okay, it's not clear what's going on here, but what if I zoom in more? You will see what's happening here. Okay, right? So you can see this wave. Yeah, let's if we ignore the amplitude, okay, the amplitude of this modulation, we can see here for 399 hertz, it's near half of the sampling rate, right? Then it's just all these alternating points, right? Alternating points of just basically you only have 2 points to represent each cycle. Therefore, it has this alternating kind of patterns in this sampling. Okay. So you can hear it's barely representing the sound. Okay. But if we change the rate to this, oh, it's the same. So yeah, it's not a good way to do it. Let me do this, change this back. But whatever. I'm not going to try this out because it's the same audacity, it's the same result. So yeah, let me delete this. Actually, what you just saw here, right? This is actually the amplitude modulation. If you remember what we just talked about in our last class, right? When we talk about modulation, this is amplitude modulation. It's the same shape as this amplitude modulation. And we will continue with this video, and this author will explain to you why this amplitude modulation will be presented here, right? It's just it's a kind of system bug, I would say. It depends on how the people design this audacity, this audio processing system. So yeah, so this is actually amplitude modulation, and this is actually called beating. So I will continue with this video, and you will see more about this. But I think the fascinating thing, I mean, I really encourage you to try this out by yourself, okay, using Audacity. You can choose some frequency just lower than half of the sampling rate, and you just increase the sampling rate. You can see whatever the waveform looks like, the tune or what you hear will be exactly the same. Okay, so those tunes are exactly the same. Let me play this again.
99 hertz, it offers no advantage. I'll repeat the same exercise for much higher sampling rates, first at 96,000 hertz, and then at the preposterously high 192,000 hertz. And I'll lay them all together so you can hear the difference for yourself. Convinced yet that there's no difference? Audibly, there is no difference. But viewing the waveform, it's dodgy, alright? Now let's explore why this is the case. For one thing, we've been viewing the waveform all wrong. We don't just linearly interpolate between two data points and put a straight line between them. This is an inaccurate representation. Let's fix that. We're back in the project with 11,025 Hz as the sample rate. We'll go to Edit, Preferences, Tracks, and then we'll change the display samples to stem plot. Much better, because this is exactly what we have in the digital domain, discrete data points and nothing else. Now, when the time arrives when this digital signal needs to be converted into an analog signal for us to listen to, it goes through a series of electronic circuits. In the simplest case, it goes through a resistor ladder circuit. And without unnecessarily complicating this video, it produces a stair-step pattern of an intermediate analog signal. So our data points.
Okay, so here is a standard explanation why the different kind of shapes of waves produce the same tune.
Are turned into an analog signal, which looks like this. This isn't the final output signal yet. In this form, the analog signal has a lot of super high frequency components. Some would even be ultrasonic frequency components, which we can't even hear. How would you tell this? Well, it's not clearly evident from the waveform what the exact frequencies are, but whenever a time domain signal shifts almost instantaneously like this, it means that the cone of the speaker would have to resonate and vibrate according to the signal and move its cone really, really fast. When events like this occur once in a while, it's usually perceived as clicks and noise. But if it tends to repeat periodically, you're likely to get a high frequency tone. And the frequency would depend on the slope and height of such shifts. In a complex real-world input signal, you would end up getting a complex spectrum of high-frequency components in the intermediate signal. The obvious thing to do would be to cut off these excess frequencies and discard them. And the most obvious place to start would be all the frequencies above half the sample rate, from which point on will be referred to as the Nyquist frequency. This is because we promised that the input signal would be band limited when it first arrived at the analog to digital conversion stage by putting a low-pass filter on it with a cutoff as the Nyquist frequency. Clearly, the output signal would need to adhere to the same rules and the same low-pass cutoff at the Nyquist frequency as well. And when the filter is applied, the intermediate signal is transformed into this, which is essentially a smoothed out version, which intersects all the points that were previously sampled. And this is where things get interesting. The signal produced that goes through all these points is a mathematically unique solution. There can only be one band-limited signal that can pass through all these points, and it is the input signal itself. So the input signal passed through the analog to digital conversion step is the only possible signal that can be produced at the output stage of the digital to analog conversion. If the output signal were to deviate even slightly from the input signal, it means that it would have to contain frequencies higher than the Nyquist frequency, and it would fail to meet the criteria put forth by the sampling theorem about band limiting. The conversion is mathematically lossless. Of course, analog components are never noise-free, and the whole process would add a little bit of noise into the signal, but if the conversions are kept to a minimum, it's never noise that can be heard by our ears. It would be stellar to see and hear the intermediate signal with all its high-frequency noise, but it's not possible because the filter right after it is baked into the DAC circuit, and you don't have an off switch to switch off the filtering. But what you can see is the output analog waveform. I can't demonstrate this to you because anything visual that I can reproduce on my computer screen is still well within the digital format, and you need specialist analog equipment to view any analog waveforms. I, unfortunately, don't have an analog oscilloscope lying around my house. But I can redirect you to this excellent video demonstration by Monty from ziff.org, where he introduces a full signal path that you can view, which can help you solidify the concepts that I'm putting forth here. The video is in the description below. Do you remember that I mentioned that the low-pass filters cannot cut off frequencies exactly at the Nyquist, but would require a smooth ramp? For this reason, we need a bit of a buffer between the highest frequency that we want to represent and the Nyquist frequency we need to completely cut off at. This gives us a clue about what could have gone wrong with the 8 kHz sampling of the 3999 signal that was amplitude modulating. Let's imagine the cutoff frequency implemented by Audacity is at 4 kHz or the Nyquist frequency. The practical limitations would not allow it to simply cut off all frequencies above that, and there will be some spillover. We know that there will be extra high frequency content because the intermediate signal will look like this. There will be a gradual reduction of the frequency content above the Nyquist, but they'll still be there. This is in direct violation with the sampling theorem, which requires there to be no frequencies above the Nyquist. But what happens when there is? We get the folding of the high frequencies at and above the Nyquist back into the original spectrum due to a phenomenon called aliasing. Clearly, aliasing puts additional frequencies into the output signal which didn't previously exist to begin with. And this is a bad thing, and we want to avoid aliasing artifacts. These extra closely represented high-frequency signals folded back onto the original signal is what causes the interfering amplitude changes. Let me demonstrate this. Let's go back to Audacity and select a new project with a pretty high sampling rate. Let's generate 2 sine tones. One is 400 Hz and the other is 401 Hz. The difference between the two signals is 1 Hz. Now let's select both the tracks, head on over to Tracks, Mix, and then mix and render to a new track. What we can see here is an acoustical phenomenon called beating. It's an interference pattern between two sounds of slightly different frequencies perceived as a periodic variation in volume. More about this in a module on acoustics. But this is essentially what's happening in our example, with aliasing ruining our output signal. So it's well worth it to have a bit of a buffer between the highest frequency we want to represent and the Nyquist frequency above which no frequencies should exist. This is why the beating effect and any aliasing vanished when we tried to represent the 3999 Hz signal on the next higher sampling rate of 11,025 Hz. This meant that there was a considerable buffer between the highest frequency content that we wanted to represent, which is 3999 Hz, and the Nyquist frequency, which is half the sampling rate at 5512.5 Hz. So for all practical intents and purposes, we want to modify the sampling theorem to suggest that instead of sampling at 2 times the highest representable frequency, we want to increase that to 2.5 times the highest representable frequency, commonly called the engineering Nyquist theorem. This is done not because of the mathematical limitations, but practical electronic limitations. I think this is a good time to step off from this video before it becomes any longer.
Yeah, I think it's already too long. So, but whatever. So this explanation, okay, so this filter, though you need this buffer, actually explains, right, why we choose this number, right, 44100 Hertz to be our standard sampling rate. Okay, so we see for human hearing, the range is 20 to 20,000, right, Hertz. So theoretically, if we follow this Nyquist sampling theorem or Nyquist limit, I would say, right, 40,000 Hertz would be enough, right? Because this 4,000 Hertz, if we have a sampling rate equals 40,000 Hertz, so theoretically we can represent everything, all the frequencies, right? So this is the graph. So this is Fs over 2. So if we have a Fs of 40,000 Hertz, then we can well represent everything between 0 to 20,000, right? And then this Fs, this sampling rate should be enough for our hearing, because human hearing is band limited. But why we choose this extra 100 here, right? Where this 1 comes from? Why we don't have, oh no, where this 4,100 comes from, right? This is a lot of hertz we actually added there. So this buffer, okay, so this buffer actually explains where this extra 4100 Hertz comes from, okay? Because if we cut like clean or cut closely on this thing, then it will cause some problem because your filter is not, you know, it doesn't cut like this. So there will be a buffer, there will be a slope that gradually cut off the frequencies. Therefore, we need to set Fs a little bit larger than 40,000 Hertz. Therefore, for this engineering Nyquist theorem, we choose this sampling rate to be our standard. Okay, our standard sampling rate for nearly every like computer digital audio system. So this explains why we have this extra kind of extra numbers, extra hertz applied here. Okay. So I think we'll take a break for 15 minutes. After that, I will continue with this topic. Okay, I'll continue with aliasing, audacity, and yeah, explain more about those concepts. Okay, see you in 15 minutes. We'll come back at 3:50. Okay,
But we've barely